Welcome back everyone. In this lecture, I will introduce the notion of irreducible root systems, and then we will see a given root system how to write that as a direct sum of irreducible root systems, and then using this we will reduce the problem of classifying root systems to classification of irreducible root systems. Okay, let us begin. We fix some notations. As before, we take phi to be a root system inside A. So, capital E is the Euclidean space in which the roots lies. So, first we define the notion reducible. So, what is reducible root system? So, phi is called reducible if phi can be written as disjoint union of phi 1 and phi 2 such that all these elements from phi 1 will be orthogonal to elements of phi 2. So, that means the inner product phi 1 phi 2 is 0. So, it symbolically this means alpha beta is 0 for all alpha in phi 1 and beta in phi 2. So, now we are ready to define what is called irreducible root system. So, irreducible root system by definition which is not reducible. So, phi is called irreducible. So, then you can see that it is not reducible if it is not reducible. So, that means whenever you write phi as disjoint union of phi 1 and phi 2. So, then there exists alpha in phi 1 and beta in phi 2 such that the inner product alpha beta must be non-zero. So, that is what irreducibility means. Okay. So, why this irreducibility naturally motivated? So, that is motivated for the following reason, that is because any given root system that can be written as direct sum of irreducible root system. Basically, we write it as disjoint union of irreducible root systems, but we just call them as direct sum. Okay. So, here the proportion. So, given this root system, we can write phi as phi 1 direct sum etc. direct sum phi k. So, that means phi 1 disjoint union etc. disjoint union phi k, where each phi i's are irreducible. Each phi I is an irreducible root system, and all these are orthogonal to each other. Phi I, phi j are orthogonal for all I not equal to j between 1 to k. So, you can write phi as disjoint union of phi 1 etc. phi k. Each phi I is actually an irreducible root system, and phi a and phi j they are orthogonal to each other for all I not equal to j. So, this is the way you can actually write any given root system. So, in this case, so we just call, so if star holds, so we say okay, so this is just a way of saying. So, we say, so phi is a direct sum of phi 1 etc. phi k if the above things holds, if star holds. Of course, star means both this phi I to be irreducible as well as phi I phi j equal to 0 whenever I not equal to 0, all these things should hold. In that case, we say phi is a direct sum of this irreducible root system phi I. So, what is the proof? Okay. So, the proof is actually uses some graph theory ideas already. So, in particularly I like this proof because you can see that already some graph theory can be used in order to prove some facts about root system. Later we will see that graph theory is what used very much in order to actually classify irreducible root systems, but anyway this is like a warm up. So, what we do, we define this graph. So, define a graph. So, this is a finite simple graph. So, that means there are no multiple edges and loops. So, we define this graph with a vertex set to be capital pi. So, all the elements of this phi are the vertices of the graph, and what are all the edges. So, for edges to be just if I take two elements alpha beta inside phi, so we draw an edge. So, we draw an edge from alpha to beta if and only if we take the inner product to be non-zero. Okay. So, now it is a fact from elementary graph theory or some or basic topology that this graph which we define, this graph we denoted by g of phi. So, this g of phi, since it is a finite graph and it is, you can draw it in R2. So, either you can use basic topology or we can use elementary ideas from graph theory to prove that this G is indeed union of connected subgraphs. Okay. So, G of pi can be written as G1 union etc. Gk. So, this is the disjoint union of Gi's. So, this is disjoint union of graphs such that each Gi is connected simple graph, connected simple graph. So, now what we do, we just take vertex set of Gi to be phi I. So, then it is clear that phi can be written as phi 1 disjoint union etc. disjoint union phi k with the property that phi I comma phi j. So, this inner product is 0 for all I not equal to j. So, the phi I and phi j, they are orthogonal to each other for all I not equal to j. So, now it is an elementary exercise to verify phi I must be a root system. So, this is something I will leave it to check. So, check that phi I is itself a root system and it must be irreducible root system, and phi I is also irreducible because the corresponding graph is actually irreducible. So, it is not very hard to see the graph of phi is connected if and only if phi is irreducible. So, this is something easy to verify. So, G of phi is connected. So, this is also I leave it as exercise, connected if and only if phi is irreducible. So, this proves that any given finite root system can be written as direct sum of irreducible root systems. But now we can actually infer many things about the root system phi if we know this the direct sum factorization. So, let us see what are all the things we know. So, if we write phi as direct sum of these irreducible root systems, then note that first of all capital E can be broken into direct sum of these subspaces spanned by this E phi i's. So, where E I is the span of phi I over R, and all these E i's, they are all orthogonal to each other. So, E I orthogonal to E j for all I not equal to j. So, then E can be written as direct sum of this E I, and moreover this phi I lies inside, this phi I lies inside E I. So, this is indeed root system on its own. So, this is actually irreducible root system. So, that is also very clear. So, now if we take this pi intersection phi I to be pi I, so then it is clear that this pi I is actually a base for this capital phi I. So, once you write phi as direct sum of phi i's, so it is clear that the corresponding Euclidean space is written as orthogonal sum of this E i's, and the base also split into orthogonal sum. So, note that pi can be written as pi 1 disjoint union etcetera disjoint union pi k, and this pi I also satisfies this orthogonality property. So, the inner product pi I pi j will be 0 for all I not equal to j, and it is indeed actually a characterization for writing phi as direct sum of phi i's. So, in case if you can write capital pi as a disjoint union of pi i's such that pi i's are orthogonal to each other. So, then you can also write phi as a direct sum of phi i's. So, that is something easy to verify. I will leave it to you to check. So, what we are getting it from this observation? So, from this observation we are getting that to classify all the root system. So, because any root system can be written as a direct sum of irreducible root system. So, it is enough to classify only irreducible root systems. So, in what follows we will use the ideas from graph theory, so called Dinkin diagrams, or some ideas from this matrix theory called Cartan matrices associated with the root system in order to classify all these irreducible root systems. Okay. So, before getting into that we need to observe some results about this irreducible root systems. So, let us make those results. So, first of all I will prove lemma capital A, this is for irreducible root system. So, if phi be irreducible root system, then one can prove that there exists unique maximal element with respect to the partial ordering that we have. Okay. So, you start with phi, so that is let us assume to be irreducible root system, be an irreducible root system. So, then there exists unique maximal element beta inside phi with respect to the partial order that we have. What is the partial order? Recall, the partial order is defined on phi. Okay. So, that is the partial order that we are using. So, lambda mu for lambda mu in phi. So, we define lambda greater than or equal to mu if and only if lambda minus mu it is sum of positive roots. That means, lambda minus mu is in z plus span of pi. So, this is the partial order. So, now this maximal element that also satisfies the following property, and all these properties will be immediate once we establish this beta is actually unique. So, what are all the properties? If we take height of beta, of course, with respect to the simple roots pi, then the height of beta will be always greater than height of alpha for all alpha in phi such that alpha not equal to beta. The second property, if we take the inner product beta alpha, that should be non-positive, non-negative for all alpha in pi. So, now what will be the third property? The third property, you write beta as summation k alpha 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 in pi. So, then we can see that all these coefficients k alpha must be positive. So, this all k alpha must be positive. So, all these properties are satisfied for this maximal root. So, let us prove this. So, how one going to prove? Of course, we have to use the condition that phi is irreducible. So, this is what we need to use. So, let us try to use that. So, this expression is somewhat very important. So, because we are claiming that k alphas are all positive. So, that motivates us to define the following sets. So, first you write beta as summation k alpha, alpha coming from pi. So, since beta is maximal with respect to the partial order, so it is clear that beta must be positive. So, clearly beta must be positive. So, in particularly we can assume that this k alphas are all coming from Z plus for all alpha in pi. So, now what we can do, we can define these two sets, let us call it pi 1 and pi 2. So, this is those alpha is in pi such that k alpha positive, and then you define pi 2 which is those alpha in pi such that this k alpha is equal to 0, because these are all the two options that we have. So, then it is clear that pi can be written as disjoint union of pi 1 and pi 2. From our earlier observation, we can see that pi 1 and pi 2 cannot be orthogonal to each other. So, that means there exists alpha inside pi 2 and alpha dash inside pi 1 such that alpha alpha dash must be non-zero. So, this must be true. Since both alpha and alpha dash they are coming from this set of simple roots pi. So, that forces that the inner product alpha alpha dash must be less than 0, because the angle between any simple roots must be obtuse, that we have already proved. So, this says something about the inner product between beta alpha. So, if you compute what is the inner product between beta alpha, you can see that this is nothing but summation, let us say k gamma gamma, gamma coming from pi times alpha. So, then you can see that gamma alpha will be always non-positive for all gamma. In particularly we can see that this will be less than or equal to k alpha dash times alpha dash comma alpha. So, since k alpha dash is actually coming from alpha dash coming from pi 1, k alpha dash must be positive and this is negative. So, that forces that beta alpha is negative. Now, what happens if beta alpha is negative? From our earlier lemma, we can see that beta plus alpha must be a root. So, this forces, because if beta alpha is non-zero and beta alpha is negative, then we know that beta plus alpha must be a root. So, that forces that this beta plus alpha is a root, which is a contradiction, because this then says that beta plus alpha is bigger than beta, but that is contradiction, since beta is a maximal root by choice. So, that means what we have proved, this actually only happened, that is because we assumed that this pi 2 is non-empty. So, because we assume this is non-empty, that is why we got this contradiction. So, that proves that pi 2 must be empty. So, that means if pi 2 empty, so that forces that pi 1 must be pi. If pi 1 is pi, that means k alpha is positive for all alpha in pi. So, this is something we already proved. Now, of course, in the course of proof, we also observe that this inner product beta alpha cannot be negative. If it is negative, then beta plus alpha must be a root. So, that also proves that the inner product beta alpha must be greater than or equal to 0 for all alpha in pi. So, this is something proves second property. So, now we verified third property and second property. Now, we need to verify the first property and as well as the uniqueness. So, let us assume there is another maximal root. Okay. So, now you can see that. So, let beta b dash to be another maximal root, of course, with respect to the partial order. So, then we can also assume that beta not equal to beta dash, otherwise we are done. Okay. Assume that beta not equal to beta dash. So, then you can see that this beta times beta dash, the inner product. So, that is going to be greater than or equal to beta comma alpha, which is positive for this alpha. Okay. What we can do, we can choose this alpha. So, there exists alpha such that inside pi such that beta dash comma alpha is positive. Okay. So, that is from our earlier observation. Okay. Other not because of our earlier observation. So, we already from our observation we already proved that for any maximal root beta the inner product beta alpha will be non-negative for all alpha in pi. So, now if beta there is no alpha such that beta dash alpha is positive, then that means beta dash will be orthogonal to alpha for all alpha in pi, but pi spans E. So, that actually contradicts the spanning of pi. So, that means there exists alpha in pi such that this beta dash alpha must be positive, since span of pi exactly equal to E. So, we get such alpha. So, for that alpha we have this inner product beta beta dash is greater than 0, but then this forces from our earlier lemma beta minus beta dash is actually a root. Then there are two choices. Choice 1, beta minus beta dash could be positive, and choice 2, beta minus beta plus beta is actually positive. So, in the first case what we get beta dash is equal to beta equal to beta dash plus beta minus beta dash. So, this forces that beta is bigger than beta dash, which is a contradiction, because both beta beta dash are chosen to be maximal elements and beta is not equal to beta dash. And the second case beta dash minus beta is being in phi plus implies that beta dash can be written as beta plus beta dash minus beta. So, that forces that beta dash is bigger than beta. Again we get a contradiction because both are maximal and they are distinct. So, this proves that there is no other maximal element different from beta. So, that forces that there exists unique beta maximal inside phi. Okay. So, now I will leave it to you to check in this case. So, we also have this height of beta is greater than height of alpha. For example, if alpha is negative, then since beta is positive, height of beta must be always greater than the negative number. So, there is no issue. If alpha is positive, then height of beta is same as height of alpha. So, then that will forces that beta equal to alpha. So, since beta not equal to alpha and beta minus alpha is actually sum of positive roots. So, that forces that height of beta must be strictly greater than height of alpha for all alpha not equal to beta. So, that proves the first condition. So, in particularly we have this maximal root, unique maximal root. Okay, we will observe something about the maximal root later. For that purpose, we need to actually observe something about the while group action on this capital E. So, let us see what we can say. So, here is the lemma B again for irreducible root system. Let phi be an irreducible root system. So, and with the while group let us say W. So, then W naturally acts on E. Okay. W acts on E. So, what we want to claim, it acts irreducibly on E, irreducibly on capital E. So, what is the meaning of that? So, as a representation W representation, E is actually irreducible module. So, E is irreducible W representation. So, that is what we mean by W acts irreducibly on capital E. Note that the W is finite group. So, any finite dimensional representation of W must be direct sum of irreducible representation using Mastek's theorem, okay, which we are not going to prove now, we just assume. Okay. So, in particularly if you choose any alpha in phi, then the span of W alpha must be E. Okay. In particular, span of any orbit of W alpha over real must be equal to E for all alpha in phi. Okay. So, this is immediate corollary. Okay. So, let us prove this. So, to prove that W acts irreducibly on E, what we need to prove, the only W invariant subspaces of E are nothing but E and 0 itself. So, we start with non-zero subspace and then we try to prove that that subspace which is W invariant is equal to capital E. Okay, let us start with E dash, which is a non-zero subspace of E, and then we also assume that E dash is W subrepresentation. That means E dash is W invariant. So, now since W is a finite group, as I said, we have complete reducibility for finite dimensional representations of W. Since E is actually finite dimensional space, so then we must have a complementary W subrepresentation of E dash inside E. So, call that is E double dash. So, this is a complementary W sub representation of E for this subrepresentation E dash. That means E can be written as E dash direct sum E double dash. So, now note that for any given alpha inside phi, you can see that either alpha is inside E dash or else E dash is inside P alpha. So, either alpha is inside E dash or E dash is completely contained in P alpha. So, why this is true? So, for example, you can assume alpha not equal to alpha does not belongs to E dash, and then let x is inside capital E dash. So, let us say this is what you have. So, then if you apply S alpha of x, then we get this is exactly equal to x minus twice x alpha divided by alpha alpha alpha. Now, since E dash is W invariant, so S alpha of x must be again inside E dash. So, that is because E dash is W invariant and x is in E dash. So, then this forces that this x alpha, the inner product must be 0, otherwise what will happen, this term will be non-zero. Since x is inside and this sum is inside, that forces that alpha is inside E dash, but we assume that alpha is not in E dash. So, that means we get immediately x is inside P alpha. So, that forces that E dash is subset of P alpha. Okay. So, now we can see that this also implies if alpha is not in E dash for this alpha in phi, so then we should have alpha is inside E double dash. Otherwise, what will happen if suppose alpha is not in E double dash, if this is the case otherwise. So, then from earlier argument, since E W dash is also W invariant subspace, so then we get E double dash is also subset of P alpha. Then both E dash and E double dash both are subset of P alpha, that forces that E is subset of P alphas, which is absurd because P alpha is n minus 1 dimensional space or L minus 1 dimensional space and E is L dimensional space. So, P alpha is proper subspace of E, that actually gives us contradiction. So, that means whenever alpha is not in E dash, that forces that alpha is in E double dash. So, then this actually kind of breaks phi into two disjoint sets. One is coming from roots from E dash and then disjoint union roots coming from E double dash. So, now note that phi is written as disjoint union of phi intersection E dash and phi intersection E double dash. Now, since phi irreducible, you can see that, so this is going to be like, okay, we need to verify this is actually orthogonal decomposition. Okay, then that proves that phi cannot be written as direct sum of these these orthogonal subsets. So, okay, let us see what happens if we take elements from E dash and E double dash. Okay. If alpha is here and then beta is here, so then you can actually look at S alpha of beta. So, then that gives us beta minus twice beta alpha divided by alpha alpha alpha. So, this is going to be again inside E double dash because beta is in E double dash and E double dash is W invariant. So, then this forces that beta alpha must be 0, otherwise alpha will be in E double dash, but alpha is coming from phi intersection E dash, both are disjoint. So, that forces that phi intersection E dash is orthogonal to phi intersection E double dash, and this gives reducible. This proves that phi is reducible, which is contradiction because phi is assumed to be irreducible. So, in particularly we get E dash equal to E, otherwise we are getting contradiction. Okay. So, this proves that the action of W on this Euclidean space is actually irreducible action. Okay. In particularly if I take any alpha or any non-zero vector in E and then take W orbit of that non-zero vector, that must actually span this capital E. So, these results again can be used in order to prove, in order to understand the vectors that are lying inside given irreducible root system. So, indeed what we will prove that given irreducible root system, we can prove that at most two root lengths that can occur inside that irreducible root system. So, what is root length? Root length is just the norm of alpha for some alpha in phi. Okay. So, if you take this norm alpha where alpha varies from phi, then sometimes norm alpha can be equal to norm beta, that is what we have seen. From the two dimensional examples, it is clear that only two root lengths are occurring. Okay. So, that is what we are going to prove it for any irreducible root system, and we also prove that all roots of a given length, if alpha beta they have same length, then they must be conjugate under the Weil group action. Okay. Again these results are very important in order to actually understand more about irreducible root system. Maybe we are running out of time now. So, I will do this proof of these results in the next lecture. Thank you.